say that an expression a plus b is redundant if it is evaluated multiple times with the same values of the operands. And redundancy elimination is a very fundamental and important part of code optimization for compilers. And there are different algorithms for doing that, and we will start with something called global with value numbering, and there are two versions of it. One that is used during translation to SSA form, and another which is done after. Okay, so what it means is that each expression is given a number that's basically a hash table index, and then the same expression can be looked up during the translation to SSA form and see if it has already been if it exists, and if it does, with the same versions of the operands and the same operator, of course, and the same types, then we can reuse the destination of the found expression and use that instead of the new expression. Okay, and this is very nice to do on SSA form during the translation to SSA form. That is when we traverse the Dominator tree. Let's see why. If we go back to the Dominator tree, so say there is an expression a plus b here, and we can say a1 plus b2. Okay, so we put that in a table, and then somewhere down in the code we here say we are just translating a plus b and find that the correct indices are a1 and b2. Okay, then we can look at the tables in each of the ancestor in the Dominator tree, and eventually we will find this expression. So say we had t, well, it's sufficient to say t, and then we can replace that with the use of t instead. Okay, so here we can say this is the same idea, but we look at the more concrete code and not the Dominator tree. But I wanted to show that we use the Dominator tree. Okay, so here we have the same versions, and that one will be replaced with C0 and that one as well. Okay, okay, that's fine. And here, what happens here? We compute this one, and we can replace it there, and we can replace it here, and here it will not be reused since it is a different version of A. So it's no problem that it would use an expression that is not the same, and that is also the case in this. So both the operator and the operand versions must be the same. And here, say we have this expression and put it in a table, and then we come to this expression. Is there a risk that we think we should use D0 here? Well, why not use D0? D0, we have already put this one in a table. Well, that's not a good idea, so let's not do it. But if we look at the Dominator tree for this code, it looks like this, and like that, and like that. So this can be number 2, number 3, and number 4. And when we are here, that means here, we put this expression in the table. But when in a table for this vertex, and when we are here, we will not check the table for that vertex, since it's not an ancestor in the Dominator tree. And in fact, when we realize that there is no child to this vertex, there is none, and we have processed all the instructions here, then we will we don't need the table for this vertex any longer. Okay, so it is removed. Okay. Now we will look at the other form of value numbering, which is capable of handling loops as well. And so what is the purpose of this? It is to what this will show is that the compiler can conclude that x and y have the same values despite they are not assigned to each other. They start with the same values, and then they are incremented by the same value, so they must continue to have the same value. And then since the assignment to x dominates the assignments to y, y can be removed, and we can just return x plus x instead of x plus y. And of course the compiler can remove this one as well. Actually, what it does when it gives a variable place in the stack, first of all, these variables would not have a memory location, since they would probably be assigned to a register, but assume we don't have registers. What the compiler does is not to give address in the stack based on all the declared parameters or local variables. Instead, it sees which variables remain after optimization, and then it gives the stack locations. That is the addresses of local variables. So this is quite a powerful optimization, and I will not go into any detail how it works, but the basic idea is to assume that all instructions with a certain operator produce the same value. So from the beginning, the algorithm thinks that all add instructions produce the same value. They clearly don't, but it still thinks that. And then it adjusts its knowledge to remove certain, and all add instructions are partitioned into different subsets of the set of all add instructions, so that all adds in the same subset, when it's finished with this, produce the same value. And then every instruction in a subset produce the same value, and it can check if one dominates the other and remove the others. So this is quite nice. Okay, what this cannot do is to take to move code out of loops, and it cannot deal with so-called partial redundancies as well. What is a partial redundancy? Well, here we have a full redundancy. Okay, let's give a simpler example of a full redundancy. If we have a plus b and later a plus b, then it is called a full. That was not so nice. A plus b, it's a bit lagging. A plus b. This is a full redundancy, since there is absolutely no doubt that if we evaluate that one, we will also evaluate that one. But what we will see now is it's cases where this is not the case. Okay, so a partial redundancy is for instance, like this, if we have a plus b here, and then a plus b here, and some other code, then this a plus b is redundant only if we go in that direction and not if we go that direction. And value numbering cannot optimize this, but partial redundancy can, and it can do some other nice things as well. You may say that it would be much better to remove both of them and put a plus b here. That may be the case depending on how big these areas are. Because if we put this in a register for all this time and use it here, then we occupy this register and cannot use it for anything else. And if this part is consists of too many instructions, then it's a waste to reserve this register for a certain, so that we cannot use it for anything else. So therefore, what we actually want to do is to put the extra a plus b here instead during partial redundancy elimination, so that we don't occupy this register during so long time. Okay, I should also say it is not partial redundancy elimination or any other algorithm on SSA form that assign which register is used. It is still the same. There are no registers during SSA optimizations. They are done. Assigning registers is done later. Okay, there is a long history, and if you're interested, you can pause and read it, but I will not do it. Well, we can make one observation, namely that Fred Shaw, he improved PRE, and he was involved in the MIPS-X project at Stanford, and meaning the code that you saw in lab 6 about optimizing compilers was part of his experiments. Okay, and as his PhD, he wrote a complete optimizing compiler for their MIPS machine. Okay. Well, I can say one more thing, which is quite a nice curiosity, namely that there was a famous researcher who stated that PRE cannot be done on SSA form, since PRE is about expressions and SSA form is about variables. And this is good to remember. Actually, this company, Silicon Graphics, they did all their optimizations, scalar optimizations on SSA form, then switched to non-SSA form, did PRE, and then converted the result back to SSA form. So this was unnecessary. It would be nicer to have everything on SSA form. And that is how they do that is what we will see next. Okay, so their algorithm is called SSA Pre. Okay, so value numbering cannot handle this, since there is no full redundancy. It's not the same indices of the on these operands, so it will not regard them as identical values, and they are not identical values. But with the SSA Pre, there is a very nice insight, namely that an evaluation of an expression can be seen as an assignment to a special variable. Well, not very special, but a new variable. It's called H, which stands for hypothetical variable. So there is an assignment whenever we evaluate the same expression. and that means we have phi functions for. I mean, since we have assignments to this variable, we also need phi functions. I have not said why or when we need phi functions, but I just mentioned informally that we need them when there is a branch and different paths join. Okay, and here comes the cool trick, namely to say that when we destroy the value of the expression by reassigning an operand of the expression, we can say that we actually evaluate the expression and we give it this special bottom value, which of course is a completely meaningless value. It doesn't exist since we have just overwritten and destroyed the evaluation. But this assignment to h results in that we need a phi function for h in this vertex, okay, in this node or basic block. Okay, so what does that mean? Well, we have to put a phi function here, and what we can do then is to check phi function operands which have a bottom value. And if there is a bottom value, then it may be a good idea to insert the expression instead of this bottom. So what will happen here is that we will put a plus b there and the proper versions of the variables. I will not go into the details about this, but this is quite nice to first see that it can be done on SSA form, and secondly know that such partial redundancies are optimized. Otherwise, we may be tempted to change the source code to handle this, but we don't have to. Just let the compiler do it. Okay, I should also say another thing about SSA Pre, namely that it can move code out of loops. Since, well, if we have this loop, we can have an expression here and a plus b, and there is a loop, and here we go, and we may leave the loop. Okay, so there is an assignment here, and what this happens is that there will be a phi function for h there as well. Okay, why? Well, there are two assignments. There are two versions of this that reach this vertex. Okay, and this phi function here, it has I write it here instead. It has a bottom operand, and then it has this operand. So what SSA Pre will do is to insert a plus b here, and now all of a sudden this instance of a plus b has become fully redundant and can be removed. So SSA Pre can move code out of loops without even knowing there are loops, and that's quite nice. Again, the purpose is not at all to see how this is done. This is just a curiosity, but that code that is constant within the loop is moved out of loops, so we don't have to do it ourselves. Okay, operator strength reduction. This is typically translated to a plus I times 8. Okay, and what we want to do is to get rid of this multiplication and essentially get this code instead. So P will point into this array and step one element at a time forward until it reaches the end. And that can be done automatically. So this is just don't do it. Okay, so what we will do now is to see how this is done. Okay, first I mentioned in a previous video that this is invalid. And if you don't remember and are interested, you can check it, but I will not repeat it here. Okay, so this optimization, it has two names: operator strength reduction, and it means reducing the cost of the operation from an expensive to a cheaper one. Another name is induction variable elimination. And basically, well, now it's not a double, so it's 4, but it doesn't matter. What we do is to rewrite this into, well, we identify that the value of I is predictable for the future iterations since it is incremented by 1. And therefore, S is also predictable. So we can rewrite this quite easily as add instructions. Whenever we add to I, we also add to this new variable S. Okay? And then we can rewrite the expression to terminate the loop and use S instead, so I is not needed. And the reason why that is a good idea is that we get another register available. Okay, so let's now see how this is done on SSA form. First, we have the control flow graph, and then we also create a graph of called the SSA graph with the instructions as nodes, and there is an edge from an instruction to another instruction when some instruction uses the value from the other instruction. Okay, so this is the SSA graph for this loop. We can look at X, for instance. It has a phi function. It gets one operand from the 0 value. And then it gets the other operand from this add. Okay, so this is the x1, namely the one assigned in the phi function. And then one operand from this constant and the other operand from this one. Okay, so we can create a graph of all the dependencies in this SSA. I mean, there are the dependencies in the SSA graph. Okay, so what we will do now is to use another algorithm invented by Robotarian, which you may recall from algorithms, data structures, and complexity. If you took that course when I taught it. Okay, and what it does is to discover all the strongly connected components in a directed graph. A strongly connected component is a subset of the graph. So, for instance, this one, where there is a path from every node to every other node. Okay, so why is this useful? Well, what we want to do is to get rid of this multiplication. And now we will start this, we will use Tarian's algorithm and find all the strongly connected components. And we can start in any vertex, and eventually we will come here, and this I variable is a so-called induction variable, namely a variable with which is incremented by a constant in the loop. Okay, so when we see that I is an induction variable, then we see that we may be able to optimize away the multiplication by copying this strongly connected component and adapting it to what we want. As a matter of fact, this one is not necessarily a constant. It is sufficient that it's a region constant, namely that it doesn't change within the loop. Okay. If it doesn't, I mean, it could be just a variable x, and although we don't know the exact values, but we can still use this. Okay, so I will go through this rather quickly, and I will absolutely not ask anything about Tyrant's algorithm in this course, of course, but this is an illustration of how this is done in optimizing compilers. So we continue, and okay, now we have come to this one, and then we process. We follow the operands and process the strongly connected components one at a time. Okay, and now we have finished that one, and eventually we have finished this one. Okay, so this is a strongly connected component, and it is suitable for use as an induction variable. I mean, we can classify this by checking that it's incremented by a region constant, and in this case a real constant as well. Okay, so therefore this I, or this strongly connected component, is represent an induction variable. Okay, so what we want to do is to replace this one, and what we can do is to copy this strongly connected component by recursively going through each node in it. Okay, so we copy it and let another variable be used instead of T1. Instead we use this one. So whenever we incremented, I mean when we incremented I here, we increment y with this constant here. Okay, and initialize it with I times the initial value, which of course also is 0. So what the program now looks like is it contains these parts, and these parts are still in the control flow graph and still in the memory of the compiler, but they can actually be removed, as we will see how that is done later. Okay. What we also can do, but will not show here, is that we can do similar operations for this one, so that we end up with only one pointer, as we had in the pointer code for the loop.